All right, let's start. Good morning. How was the midterm? Kind of, sort of. I tried to make it shorter this time, but yeah. I haven't started grading them, but as usual, I'm going to try to be as lenient as possible. Okay. Now, this week and next week are going to be about the fundamental theorems of calculus and the Taylor approximation, respectively. Oh, I should mention, if you look at the syllabus on Canvas, I made a small change on the tentative schedule. So last week was sort of the mean value theorem week, and this week is going to be the fundamental theorem of calculus week. Next week is going to be the Taylor approximation week. And instead of having 3 weeks rather, reserved for series and analytic functions, we're going to have 2 of them. So I thought that would be good. In my experience, in this class, at the end of next week, sort of burnout starts to kick in with the students, and it's like the last part of the course ends up being rather hard to keep track of. And that's one of the reasons why I sort of I'm putting Taylor approximation before real analytic functions. Because if you look at the textbook, Taylor approximation is like the last topic. So I'm sort of changing it because of that. I really want you to understand this Taylor approximation business and this fundamental theorem business as well. So today we're going to take our time, do some review, some sort of a review at least. And then if time permits, we're going to at least state the first fundamental theorem of calculus. So ultimately, we're going to have 2 fundamental theorems of calculus, FTC1, FTC2. I looked around, by the way, regarding these numbers. There is no universal sort of consensus as to which one is the first fundamental theorem and which one is the second fundamental theorem. I'm just going to follow Taylor. For Taylor, first fundamental theorem is, well, if you differentiate, or rather, if you integrate a derivative, you should get back the function evaluated at the endpoints. I'm just pretending that we're in Calc 1 for now. We're not worrying about the assumptions and everything. FTC1 is going to be something like this, okay? So it's going to be about integrating a derivative. On the other hand, FTC2 is going to be the other way around. Namely, we would want to start with an f, integrate it from alpha, let's say, to x. So now this is a function of x. And when we differentiate this further, we want to get back, we want to recover whatever is inside. So on the one hand, even though FTC1 is integrating a derivative, FTC2 is differentiating an integral. Okay. Okay. Now at this point, this is sort of the Calc 1 approach, perhaps. But now that we have discussed all these different ideas in a rather rigorous fashion, there are many things to be determined. So right from the get-go, perhaps you would want to say, well, first of all, what is this alpha to beta? We need to define this. Because so far, we wrote things like integral on this closed and bounded interval. That this is a slightly different notation. You've probably not seen this in Calc 1. This you've seen, so somehow we need to relate this to this. So what we've been using so far is what is called an unsigned integral. I'm going to discuss all this. But in fact, for FTC1 and FTC2 too, it's often better to phrase them in terms of what are called signed integrals. So far, the types of integrals were unsigned. I'll write it as a sort of teaser. Unsigned integrals, from a physical point of view, correspond to things like mass or center of gravity. Okay, so on the other hand, these are going to be signed integrals. And so for signed integrals, so from a physical point of view, signed integrals really correspond to the net work done. Okay, when you integrate the force, you get the net work done. Okay. So mass, for instance, can never be a negative number, at least within classical physics. On the other hand, work can be negative. Okay. What is, of course, fascinating is that Newton realized that essentially both of these are pretty much the same, at least from a mathematical point of view. Okay, we'll talk about all this. So we need to figure out what this alpha to beta integral is. Another thing we should be worried about probably is, well, the regularity of this f prime. At this point, we know you don't get to just integrate whatever function you have. And probably in which sense this f prime is integrable is going to be related to in which sense of an integral this is. Okay, so we've seen so far 5 billion different senses of integrals. So we need to relate these somehow. What else? Well, these are pretty much the only two things that we need to discuss ultimately. Okay, so as usual, I is a non-empty and open interval. I'm not going to take a j this time. Remember, what we were trying to do was, first of all, we focused on integral calculus. We were only doing sort of integral calculus for functions defined on closed and bounded intervals. Right? That's what I told you. The natural habitat for integral calculus is, compact sets, compact or closed and bounded intervals. On the other hand, when we transition to differential calculus, now we only looked at functions defined in open and open intervals, not even necessarily bounded. It's not that you can't do it the other way around. It's just that sort of theory ends up being, it ends up coming nicer if you think of it that way. And then, well, I define these locally integrable functions. I'm going to remind you those as well. The point of all this is going to be, well, now we want to bring differential calculus and integral calculus together. Okay. So the first idea, this is something that I had defined also. If I have a function f defined on my interval I, taking real values, an antiderivative, it's the same thing as a primitive, okay? AKA indefinite integral. If you go back, when I define these things, I always said unsigned, comma, definite, okay? Indefinite integral is an antiderivative. It's the same thing as an antiderivative. In Calc 1, probably you've seen integral. So you would have something like this, and then they would write plus a c. Okay, c is an arbitrary constant. So that is short for, this is some function whose derivative is f. Right? Same thing as antiderivative, same thing as primitive. AKA indefinite integral of f is a function. I'll use the capital letter f. Capital F. It's a function. Just do it here, such that I'll be explicit for any x in, such that capital F, I'll write it like this. For any x in I, f is differentiable at x, and its derivative is the value of lowercase f. Okay. This is also the definition that you're going to need for the problem set due this Friday. Now, what is confusing here is, well, maybe I should say it like this. In a second, I'm going to give an example. If you want to be more accurate, probably you want to call this an antiderivative in the classical sense. Okay? In the strong sense or in the classical sense. So. Classical or strong sense. Okay. And ultimately, part of it is because it turns out that if you look for antiderivatives in this sense, well, there aren't that many in general. There are many functions for which you want antiderivatives in applications, but they don't have antiderivatives in this sense. So what you end up doing is you typically sort of relax this condition. You say, OK, maybe not for all x's in I this happens, but for most of them it happens, whatever. I'm going to give an example in a second. So those would be sort of weak antiderivatives, or weak primitives, whatever. In differential equations, you would have classical solutions. If you have a differential equation, if you can find a solution that is differentiable everywhere, such that it satisfies the equation everywhere, that would be a classical solution. But there are other solutions in principle that satisfy the equation that you're given only for most points. For typical points, it satisfies. Okay? And so, especially starting from the last century, sort of sciences transition to these weaker solutions because they're just, they're much more ubiquitous compared to classical solutions. Okay, so now I'm going to say this. Okay, I'm going to call f Newton integrable if it has an antiderivative. N of I comma r is going to be the set of all Newton integrable functions. As usual, you know by now that I immediately like to sort of define a set of functions given any property. Functions on I taking real values. If f is an n, I'm going to define its unsigned unsigned Newton integral like so. I'll take a Newton integrable function and a compact subinterval. Then the unsigned and definite Newton integral of f on k then the unsigned indefinite Newton integral of f on k is, this is our notation, right? Integration, but in the sense of Newton, over k. Well, this is just going to be capital F of max of k minus capital F of min of k, where capital F is any antiderivative. Okay. Now, first of all, this is a well-defined thing. Okay? Given any Newton integrable function and given any interval, this right-hand side is an expression, it's a numerical value that is independent of this capital F. Why? Because last week we had talked about one of these consequences of the mean value theorem. I'll write it here. Remark. Is well defined. In this context, well defined means it doesn't depend on this capital F. It seems to depend a priori. So it seems like this doesn't define a unique number, but it does. The reason is why. The reason is this. If I have two distinct antiderivatives, well, look at their difference function. I know that the difference of any two differentiable functions is differentiable. And if I differentiate this, right, this is f1 prime minus f2 prime. But I'm assuming that both of these are antiderivatives of f. In other words, f1 prime is f, lowercase f, and f2 prime is also lowercase f, which means this is 0. So whatever this function is, the difference of two antiderivatives, its derivative is 0. But furthermore, this is a function defined on an interval. We talked about how a differentiable function defined on an open interval is constant if and only if its derivative is 0, which means that any two antiderivatives differ up to a constant. Okay? But if they do differ up to a constant, this is not going to depend on f1 or f2. So I'll write it here. So by, I think this was maybe it was a corollary or a theorem, whatever, by a consequence, let's say, of mean value theorem, there's a unique C in reals such that for any x in I, f1x equals f2x plus a constant. But then, you see, this expression and this minus this equals, well, f2 of max of k plus c minus f2 of min of k minus c, but these two cancel out. And so the right-hand side, as you see, doesn't depend on which antiderivative you choose. That's what I mean when I say this integration, this Newton integral, for Newton integrable functions is well defined. From a physical point of view, what does this correspond to? Well, this antiderivative, OK, let me put it this way. If you start with a lowercase f, from a physical point of view, lowercase f is a force. Any antiderivative of a force is a potential, but potentials are defined up to a scalar, right? So if I'm looking at, f equals ma for, say, this thing, I can just determine whatever what its potential energy is. I can choose this to be the ground. That would give me a height. From that, I would get a potential. But I could also define it to be this floor. I could define it to be the floor of this building, whatever. Laws of physics, calculations and stuff would work just the same. OK? So somehow, Newton integrals is integration according to Newton. And baked into it is the laws of classical physics, and vice versa. Any comments or questions about this so far? Yes?
Is a small f and big F both are defined from the integral?
Yes.
To R?
Yes.
And their relationship is just like neighbors, right? A subset.
What do you mean?
So if this is a very big set, and they are all in the set,
I mean, you mean the set of functions?
domain. They have the same domain.
Yes.
I.
Yes, it could be a small domain, it could be a large domain, but it's the same domain.
And they both project to R, at the map to R.
Yes, they both map to R, yes.
You were talking about their relationship inside domain.
I mean, is that what you mean when you look at this? This is how they're related.
Yeah, so big F is also defined from I to R.
Exactly, yes.
Like small f.
Yeah, exactly, yes. Yes. Any other comments or questions? OK. Now I'm going to say a couple of words about this Newton integrability, how it kind of makes sense to talk about it separately compared to other integration theories. Because when you think about it, Riemann, or pretty much anyone else who came out, who sort of did work in this stuff, came much after than Newton. Okay? And in fact, when you think about it, Newton integrals are defined so that the fundamental theorem of calculus holds. It's like an axiom, in fact. For Newton, fundamental theorem of calculus is nothing but the obvious thing that should be true. So Newton, of course, he had this physical intuition, and he knew what had to be true, and he was working backwards. Right? He was figuring out what the math should be. And then afterwards, well, there were mathematicians who were more of a more mathematically inclined compared to sort of physically inclined. Not to shade Riemann on other people, and they really wanted to make sense of this integration as a thing on its own, which I'm going to try to justify in a second using examples. So this is the situation for now. We have this new sense of integrability. This is, in a sense, the pragmatic approach. For Newton, you say, well, this integral business, I'm just going to take the integrals of things I know are derivatives to begin with. And so we're going to see certain problems with this, even though it is, generally speaking, rather useful. First, I want to mention something about this classical sense. Here's a first example. Consider this. Yeah, I'll just do it like so. Oh, yeah, that's open. This is your lowercase f. Your I is -1 to 1, open. Okay. Your lowercase f is from I to r. That takes x, it's a step function, to -1 if x is non-positive, plus otherwise, or +1 otherwise. Now, in the problem set due this Friday, you're going to argue at some point that this guy is not Newton integrable. In other words, this has no antiderivatives, because you're going to see any Newton integrable function, any function that is a derivative of some other function, has to satisfy the intermediate value property. So you cannot have these type of jumps. Okay? So this guy has no classical antiderivative. Okay? It's not Newton integrable. Okay. But from the perspective of applications, this is certainly this should be a valid forcing function. Imagine that the horizontal axis is time. You're saying, I have some system, and remember, this lowercase f, from the physical point of view, from the application's point of view, is going to be the right-hand side of the ODE, which means it's the forcing function. You're saying, I have the system at equilibrium. Until time 0, I'm pulling it in this direction by 1 unit constantly. And at time 1, I'm immediately starting to pull it in the other direction. Now, you would say, in practice, you cannot just teleport. Your force is like this. So in a sense, this is somewhat idealized. But you ask an electrical engineer, and they say, OK, so I see this in my graphs. The fact of the matter is that things happen so fast is that your sensors don't quite detect how fast this jumps. Okay? But in any event, from an application purposes, you would like to be able to say to your applied mathematician or applied scientist, or scientists in general, oh, here's an antiderivative for this. Like I said, this has no classical antiderivative, but based on the needs of sciences at large, well, we look for generalizations, derivatives in weaker senses. And when you think about it that way, you say this, perhaps. If I'm looking for a function, capital F, whose derivative is this, well, for x negative, this is at -1, OK? So it should be a function whose graph has slope -1. OK? Obviously, I'm not going to look at the derivative at 0, because left and right derivatives don't match. There's no way this guy is going to be differentiable at this point. But it's only one point. Never mind that point. And when x is positive, well, it's going to have a graph whose slope is 1. So you see, what you can do is you can take a function like so. Here, you're going to have a line segment of slope -1. Okay. In between, you can choose whatever point you want, because you're not even going to look at the derivative there. And here, you're going to look at some line segment of slope 1. Okay? So in a sense, you would want to call this the antiderivative, or an antiderivative for this. But as you see, this is not a classical antiderivative. And certainly, this piece is independent from this piece, which itself is independent from the middle point. Certainly, it is not the case that any two antiderivatives differ up to a constant, which was the case in the classical sense. Okay? So you would call this, for instance, any such function, a weak antiderivative. I'm saying this because in some textbooks, even at the undergraduate level, you might see people calling this a primitive or antiderivative, but this is sort of like a generalized sense compared to what we're using here. We're focusing on the classical theory. It's not that, it's significantly, it's too complicated and you wouldn't understand it, whatever. It's just that it takes more time. There are technicalities. We would need to develop integral theory more. So I'm just bypassing that. Once you learn more analysis, eventually you're going to, all you're going to look into are going to be things like this. Okay? And so for instance, what I can do here also is that if I assume, if I say I'm going to look at a weak antiderivative that is also continuous, then these, all three of these parts have to match, right? So this part has to, so this point has to be where this ends, and this point has to be where this ends also. But again, that continuous antiderivative, weak antiderivative, would not be differentiable everywhere. Instead, it would be differentiable almost everywhere. So almost surely, it would be differentiable. Okay, but these are sort of more advanced notions. We're just focusing on the classical sense, which means that it's in the strong sense, things are a lot more rigid. So we're not allowing things like this. Okay, at least for us, yeah.
So when we want to derive antiderivative
Yes.
from derivative,
Yes.
which is an open interval,
Yes.
and we ended up with an open interval
Exactly.
as well.
Yes.
When it's an open interval, how are you able to calculate that? So you put x, always have to be a little bit off the limit, right?
Yes, ultimately. Instead of open interval, you can just take the whole reals. If that's going to help you. Because reals, you can choose I to be the whole reals. Reals, it's an open interval, is an open interval. If that helps you. And of course, what it is that this open interval property ultimately allows me to extend it just a little bit if needed. All of these functions I can extend to a slightly larger interval if I want. So because I'm choosing always open intervals, ultimately I'm sort of bypassing a lot of boundary condition type of issues, actually. Yeah. These are important things, of course, but at least at this level, it's good to sort of bypass certain technicalities. Okay. So just to reiterate, when we're talking about antiderivatives, we really mean a function differentiable everywhere whose derivative is equal to the original function you started with everywhere. This is not the end of the story. It's the end of the story for us, for this class. Okay? But the moment you start doing differential equations, this ends up being not sufficient. Okay? Any comments or questions about this so far? Okay. So that was the first example. Now here's the second example. I want to give an example of a Newton integrable function that certainly is not locally Bourbaki, nor locally Riemann integrable, nor in fact locally Lebesgue. But it'll be locally HK integrable. This is the reason why we discussed HK integrals in this class. So here's the second example. going to take I to be reals, the whole thing. And let me define. You good over there? Guys got too excited for this. No, I mean, I agree. This stuff is beautiful. It's like it just works. Just works. Here's a function. Lowercase f is this. Okay? It's a piecewise defined function, but it's a really nice function, in fact. X sent to, okay, I'm going to delete this also. Write it like so. Take an x, send it to 2x cosine of 1 over x squared. At this point, you should say to yourself, oh, this is the usual suspect. There's a lot of oscillation here. There's something funny happening here already. Okay. Plus 2 over x sine of 1 over x squared. If x is not 0, 0 otherwise. Now the claim is this guy is Newton integrable. Okay? So there's a function whose derivative is this. If you're Newton, it's obvious to you perhaps, but if you're like me, you start with the antiderivative and differentiate it to get this function. So f is Newton integrable. In fact, consider capital F defined by taking x squared, or x to x squared times cosine of 1 over x squared. Probably you can get this by integrating factors or something, even if you don't see it, actually. Never mind. This function, if x is not 0, 0, if x is 0. Okay. I claim that this is differentiable everywhere, and if I differentiate it, I get lowercase f. Consequently, I was able to just ask an oracle, what is an antiderivative? Tell me, the oracle told me, this is the antiderivative. And by virtue of the fact that this is the antiderivative, this original function is Newton integrable, which means that I can Newton integrate it over any closed and bounded interval. Okay, let's take our time, verify this. We haven't done many calculations in this class, but I want to take my time today, do examples. Now, just because a function is given to you in a piecewise manner, like uppercase f, doesn't mean that this guy is discontinuous or non-differentiable, whatever, okay? And it's just that you have to verify things separately. If x is not 0, if x is far away from 0, okay, so 1 over x squared is a differentiable function. Composition of two differentiable functions is differentiable. Product of two differentiable functions is differentiable. So this uppercase f is certainly differentiable away from the origin. The suspicious point is when x is 0. We need to verify capital F is differentiable at x equals 0. Okay? And the derivative exists, and it is 0. Okay? That's what we need to prove. So I'll just say it like this, by algebra, if x is not 0, capital F prime of x exists. It's nice, and in fact, we can just go ahead and use our chain rule and product rule, whatever, to compute this expression. I'm going to leave that to you to compute. Verify that for any x non-zero, capital F prime equals lowercase f. Okay, what I need to verify, here I can't quite use algebra, product rule, whatever, at least directly, is the situation when x is 0. So capital F is differentiable at x equals 0, and furthermore, of course, I want capital F prime of 0 to be lowercase f of 0, which is 0. Okay, I'll do it here. I can use many things at this point, but let's just use the standard Calc 1 approach. How do you compute the derivative of a function at a point? Well, you just look at the ratio and take the limits. Right? So for h non-zero, I need to look at 1 over h, f of h minus f of 0. And then I'm going to take h to 0 to compute f prime of 0. What is this? Well, by definition, this is 0. And this is something else. This is 1 over h squared, cosine of 1 over h squared. Here I have h times cosine of 1 over h squared. Okay, I'm going to take h to 0 here. This cosine factor oscillates rather rapidly, but you see it doesn't matter. This is goes to 0 as h goes to 0. Okay, perfectly valid, perfectly rigorous way to verify that capital F prime of 0 is 0. So this guy is differentiable. Therefore, lowercase f is Newton integrable. Okay. And so, for instance, I can immediately say that this, in the sense of Newton, is nothing but capital F of 1 minus capital F of 0. Capital F of 1 is nothing but x, so 1 times cosine of 1. This is just cosine of 1. Maybe I should have come up with a better number. Let's just use pi here. So this is cosine of, oh, okay, I'm just going to leave it as 1. Okay, cosine of 1. Not a very nice number, but we can directly compute it. Okay? Now, here's a question. Is this function, lowercase f, Riemann integrable? Think about it a second. See, it is the derivative of some function. Okay? So it is an indefinite integral. I could have asked, is this Bourbaki integrable or locally Bourbaki integrable, whatever. Any guesses? Yeah.
Maybe not, because you have an x there, and
Okay, your colleague is suggesting in order for this function to be Bourbaki integrable or locally Bourbaki integrable or Riemann integrable, it has to be bounded, but there's a blow up here. See, as x goes to 0, this function, even so this part is fine. What happens here is you have a sine function that keeps oscillating faster and faster, and in fact the amplitude blows up to infinity also. Yes? This guy is not bounded, therefore it cannot be Riemann integrable on any interval containing the origin or containing the 0. Likewise, it cannot be Bourbaki integrable on any interval containing the origin. So this guy, you see, even though it has an antiderivative, it has an indefinite integral, you cannot just Riemann integrate it. So Riemann integration fails. So this is harder to see, but it's also not Lebesgue, locally Lebesgue integrable. Okay, so even if you had studied this more advanced integration theory, the measure theory, whatever, you're still not going to be able to integrate it, this function, even though it is an antiderivative, even though the fundamental theorem of calculus should work. Okay. But the beautiful thing that we're going to show in the first fundamental theorem is whenever you have a Newton integrable function, that is to say, whenever you have a function that has an antiderivative, that's going to be automatically HK integrable. Okay? Very good. This is amazing. We'll see. Newton integrable functions are going to be automatically HK integrable, locally HK integrable, and certainly Newton integrals are going to match with HK integrals. Okay. This is the reason why I even mentioned HK integrals. Okay. I want to give one final example, and we'll finish there. So you see, for Calc 1 purposes, this Newton integrability is nice, because whenever you're trying to integrate a function, well, you're going to try to display it as a derivative of some function to begin with. Typically, that's what you're going to do. The problem could be that if they give you something like this, you may not be able to figure out, guess, what an antiderivative should be, even if there exists one. And in fact, what can happen is, even if an antiderivative exists, you may not be able to write it explicitly. There are nasty integrals. Okay? So this is the sinc function, cardinal sine function, in other words. This just shows up in digital signal processing, for instance. Take an x, send it to sine of x divided by x, if x is not 0, 1, otherwise. Okay. It turns out that this is Newton integrable, but there are no nice closed formula for any antiderivative. So this sinc function is Newton integrable. I'll just write it like this: cardinal sine. This just shows up to be, so this function shows up in signal processing and stuff. Then you take sort of like a rectangular function and take the inverse Fourier transform of it. You get back a function like this. So this just shows up in applications. Okay. So I think these are sort of nice examples. We're going to continue tomorrow working on these fundamental theorems and stuff. Thank you. All right, let's start. Good morning. I'm going to take attendance today. So today our main goal is going to be to cover the first fundamental theorem of calculus. I'm going to slowly write everything down in a rather compact fashion. We're going to go over each and every single item. We're going to do some sort of a review as well, because I want to sort of state the fundamental theorem for all of these different notions of integration that we've seen so far. And then we're going to prove it. Tomorrow, probably, we're going to transition to the second fundamental theorem. So, as usual, I is an open and non-empty interval. Okay. Now, I want to define this symbol, this more standard symbol for integration. So I'm going to take a function f that is locally hk integrable. What does it mean for a function to be locally hk integrable on this open and non-empty interval? Well, it just means that if you were to fix any compact subinterval of I, and if you restrict your function f to that subinterval, it's going to be an integrable function. Okay, so we defined integrability only for, integrability, Bourbaki integrability, or Riemann integrability, or Lebesgue integrability, or hk integrability, initially only for functions defined on closed and bounded intervals. But certainly, I would want to think about, for instance, a sine function as it is given to me. And this, in principle, sine function is a C infinity function defined on the whole reals. It is infinitely differentiable. Okay. Of course, I can decide to choose to integrate this function on a closed and bounded interval. And that's why I want to say something like, oh, this function, it being continuous, for instance, is locally Bourbaki integrable. Right? Because any infinitely differentiable function in particular is continuous. And we know any continuous function can be uniformly approximated using step functions on any closed and bounded interval. For instance, you cannot approximate this function uniformly using steps on the whole reals. But if you restrict the sign on a closed and bounded interval, you sort of chop the function, then you can uniformly approximate. Okay, that's the whole point of local integrability. And I'm going to take 2 points, alpha and beta. They might be the same point. Alpha might be to the left or to the right of beta, whatever. And I'm going to define the signed and definite integral, or hk integral, of f from alpha to beta. Right? So the direction now matters is this. Now I'm going to use the more standard notation. Here I'm going to put a subscript, subscript, hk to represent, oh, this is the integration in the sense of hk from alpha to beta. What does this mean? Well, this is going to be the unsigned integral, hk integral of f from alpha to beta, if alpha is to the left or of beta. Otherwise, well, that means that beta is to the left of alpha, in which case I can look at this interval, integrate the function over this, but I'm going to pick up a minus sign. Okay? Of course, now at this point, so this is the same thing as, so you get to flip now the endpoints, but you pick up a minus. Okay. Why? Because you see, this is supposed to be corresponding to this physical notion of work, and work is a signed quantity. It matters in which direction you're integrating. Okay. Any comments or questions about this? It's not a significant difference at the very least in single variable, but you can imagine in multivariable calculus, this direction does matter. Say you have a vector field and you have sort of like a shape, and you're trying to compute the flux or whatever. Then it matters if you're computing things in the outward direction or the inward direction, and so on. In single variable, it doesn't matter that much. That's why, for instance, if you look at the textbook, Taylor doesn't really distinguish these two notations that much. It's not really that big of a deal, but I thought it would be a good idea to worry about these kind of matters right from the get-go. Then it becomes much easier to sort of transition to multivariable stuff. Okay, and just like this, I can also define signed and definite Newton integrals, Bourbaki integrals, Riemann integrals, or Lebesgue integrals if I so desire, and I'm going to certainly use these. It's always the same idea, okay? If you want to, for instance, define the signed, say, Riemann integral from alpha to beta, again, you're going to split into two cases. You're going to say either alpha is to the left of beta or the other way around. In any case, that gives me an interval that is closed and bounded with endpoints alpha and beta. I'm going to integrate my function in the unsigned sense, in the sense that we discussed so far. Then I'm going to put a plus or minus to the end result. I'm going to multiply it with plus 1 or minus 1, depending on whether or not alpha is to the left of beta or not. That's what you do all the time. Okay, I'm not going to write it again for these other integration theories because you just replace this symbol with one of these other symbols, ultimately. Okay. Now, I want to state the first fundamental theorem of calculus. And I'm going to state it in more and more general cases. And I think even though the most general statement that I'm going to state is going to be for HK integrals, it's going to imply all the other ones that I'm going to write before. But I thought maybe it might be a good idea to sort of discuss the same theorem, say, from the perspective of Bourbaki integrals or Riemann integrals also, just to give a review as well. So it's going to have 5 steps. Step 1 is sort of the nicest case. It says if I have a C1 function, g, okay, continuously differentiable, remember. And if I have 2 points, alpha and beta, in I, then it says that the Bourbaki integral of g prime is the same thing as the Newton integral of g prime. Okay. So let's try to parse this. I want to take my time going through the statements. Let's just only focus on item 1. If g is C1, it is continuously differentiable. G prime exists, and it is a continuous function. Okay? But also, you see, by virtue of the fact that g is an antiderivative of the function that is g prime is also Newton integrable. Okay, so this g prime is a function that is both continuous and Newton integrable. These are 2 properties that are sort of in general position, if you want. They're like this. So continuous doesn't imply Newton integrable, and nor vice versa. But you see, now we have a conundrum. By virtue of the fact that this function g prime is continuous, well, we know that continuous functions are Bourbaki integrable, or rather, maybe I should say, locally Bourbaki integrable. G prime is both locally Bourbaki and Newton. But the conundrum then is, well, we could try to integrate this using Bourbaki integration or Newton integration. Okay, these are 2 distinct senses of integration. But then the first part says, well, these 2 actually give you the same result. So integrate g prime, let's say, relative to Bourbaki. And this part says, can integrate G prime relative to Newton. Okay. Okay, so here, instead of writing it like this, maybe I'll add this as well. What is this in this case? Well, I can just write this Newton integral of G prime to be G of beta minus G of alpha, right? Because G is an antiderivative of G prime. And whenever you have something like this, the Newton integral of a function is nothing but the antiderivative evaluated at the endpoints. Okay? I'll write it like that. So this is G of beta minus G of alpha. And again, this is the Newton integral of G prime. Okay? Now, of course, at this stage, I'm still at item 1. Instead of putting here a B, I could have put there R, L, or HK. This is something that we kind of mentioned and gave in exercises and stuff. Any Bourbaki integrable function is Riemann integrable. Any Riemann integrable function is Lebesgue integrable. Any Lebesgue integrable function is HK integrable. Okay? So whichever integration theory you're most familiar with, you can put that letter here. Okay? They're all going to give you the same result. Okay? So the item 1 is the best case, you see. If I start with a G, a specified antiderivative, so to speak, and if I'm trying to integrate G prime, things are nice. Everything works, and everything gives you the same thing. Especially, for instance, if I were to start with a polynomial, okay, there's no point in discussing any of this, this says. All of these theories agree. Any comments or questions so far? Yeah.
So just excuse me for my bad memory.
Yes.
When we were talking about Bourbaki, we never introduced G beta minus G alpha.
Exactly. But we did introduce this.
Yeah, when we introduced that, we never introduced the middle.
Well, yes, but this is a definition of this. This is a definition. So this is a definition of Newton integral. That's what I'm trying to say. The point here is that, in fact, this expression is independent of G. It is uniquely defined by G prime, alpha, and beta. So that is to say, start with G, add to it, for instance, some constant. That's again C1. Its derivative is again G prime. So the Newton integral is not going to change. So this expression, in fact, doesn't depend on G, insofar as you change it among all antiderivatives of G prime.
Independent of G prime or independent of G?
Independent of G.
Really?
Yes. This was a comment that I was trying to make yesterday. Okay, so this is the point of Newton integral. So let's write it like this. It's a good idea because I'm going to sort of mention these here as well. For instance, I'll write it like this. If you start with a Newton integrable function, by definition that means there is some other function whose derivative is lowercase f. Newton integrable is the same thing as derivative of some function. Okay? That's the definition of what it means for lowercase f to be Newton integrable. I'm defining it like that. Why? Because from the perspective of Newton, Newton doesn't care about integrating any function that is not a derivative to begin with. Okay? But then, you ask Newton, what is the integral of this lowercase f? It says, oh, insofar as I have an antiderivative, this integral is going to be the antiderivative evaluated at the endpoints. According to Newton, this is the only integration that you should ever worry about.
And so it's independent of what?
Independent of the choice of capital F. Let me put it this way. You look at this and then you say, well, but then it seems like this result, this Newton integral, depends on the specific antiderivative that you're choosing. But it's not. That's the thing. Okay? Say there's another g. Such that g prime equals lowercase f again. So say you have another antiderivative. For instance, in the case of differential equations, you have many solutions. Okay, I didn't choose an initial value, for instance, here. This is just an ODE. But then, f prime is the same thing as g prime. They are both lowercase f, which means f minus g is a function whose derivative is 0. Right? The only function that is whose derivative is 0 is a constant function. Yes? Which means g is capital F plus some specified constant. Okay? But then if this is the case, if you were to look at g of beta minus g of alpha, these constants are going to cancel out, and it's going to be equal to f of beta minus f of alpha.
So it's just up to one constant difference.
Sure, but it's a big difference. So the change of c here, in terms of differential equations, correspond to changing the initial value, if you want. Yes. In this case, it's only up to a constant, by the way. Okay. So antiderivatives for the same function differ up to a constant, but this expression is independent of that constant. And so you can safely associate this number to f alpha and beta, and that would be a well-defined expression that depends only on alpha, beta, and lowercase f. It doesn't depend on capital F, even though it looks like it does.
In other words, you can also write g.
Say again?
G.
Yeah, if I wanted, I could have written it like that too, yeah.
And the difference between f and g is just a constant.
Yes. But you see, because of this ambiguity, I would say this is stylistically better. I would prefer this better, because this clearly doesn't use anything extraneous. Okay? This is, okay, it's an integral. When I see an integral, I look at the function I'm integrating, I look at the endpoints, that should give me one specified number. So that's why I prefer this expression over this expression a little bit. Okay? If you want to think of this in terms of like multivariable calculus, you can think of this lowercase f to be like a vector field. It being Newton integrable would correspond to the statement that it's the gradient of something else, for instance. But we're not going to get there. Or you might also hear the word exact. If you've heard of exact differential equations, it's the same idea. This just shows up pretty much everywhere. I'm sort of trying to build a certain narrative, okay? So the narrative is this. Newton came around and he realized what to differentiate and what it means to differentiate things. And then he did that because he wanted to use differential equations, okay? So he wanted to be able to solve them. But then people after him were like, they're trying to impress Newton, okay? Bourbaki comes around and says, oh, you can do it this way, actually. But of course, in order to impress Newton, whatever integration, no matter how bizarre it is, you come up with, it has to agree with Newton. You can do something else if you want, but then it will be more complicated. So we're just sticking to the Newtonian paradigm, if you want. All of this math is so that classical mechanics works the way it does.
So we learn Newton first in Cal 1, right?
Essentially, yes. Yes. I mean, probably you did see sort of the Riemann definition of integration, but in practice, Newton integrals are the only integrals you're using in Calc 1, for instance. I think it would be rather I feel like it would be like an outlier if you saw how to approximate integrals using Riemann sums in Calc 1, even though they kind of tell you that you can. Typically, the point of Calc 1 is you learn how to use the fundamental theorem of calculus, which means you learn Newton integrals, mostly. They don't say this, of course. They don't sort of distinguish these different types of structures, but never mind. This course is all about sort of figuring out where different parts of the whole theory comes from, ultimately. Does this kind of make sense? Any other questions here? As you can imagine, this is very important for us, so I'm taking my time giving the narrative and stuff. Okay, so this is the first item. Now I'm going to keep sort of coming up with more and more general senses. So just to reiterate, because in this case, G prime is continuous, therefore Bourbaki integrable, therefore Riemann, locally Bourbaki integrable, locally Riemann integrable, locally Lebesgue integrable, and locally HK integrable. In principle, you can put whatever letter you want here. Doesn't matter. They're always going to agree. Now we go to the next step. If I start with a function that is locally Bourbaki and Newton integrable, okay? So now I need to assume both of them simultaneously. I cannot just say, if I have a Bourbaki integrable function, it is Newton integrable. We've, in fact, seen an example yesterday, okay? Oh, well, I should say it like this. So for instance, step functions are Bourbaki integrable, but not Newton integrable. And I cannot just say Newton integrable implies Bourbaki integrable as well, and that we saw examples for. But again, the situation is the same. Now I have some function in this intersection, and so I can integrate it relative to either Bourbaki. Okay, I'm going to remind you what this means. Or I can just look at this. And again, step 2 says both integrals coincide. Now, if I wanted, I could have been more explicit in writing this, and I could have written it like this. Let f be locally Bourbaki integrable. I'll write it. I can write it more explicitly. This notation helps me sort of compress a lot of things. And I want to keep the statement on the board. So integrable, and say there is a function differentiable such that capital F is lowercase f. Okay? Then the Bourbaki integral of lowercase f is uppercase f evaluated at beta minus uppercase f evaluated at the other endpoint alpha. I could have written this. This is equivalent to writing step 2 or item 2. I just expanded it out. like I said, I prefer, instead of writing it like this, I prefer writing Bourbaki integral equals Newton integral, because why? In principle, this doesn't depend on capital F. But it is completely determined by lowercase f and alpha and beta. Okay? This is like, in a sense, probably this is some sort of a conservation of energy type of thing, actually. Sort of mathematical formalism is developed so that the things that you would expect in physics are sort of duplicated in the notation also. Okay. So I could have written it like this, and in the textbook you see something like this, a statement like this. I find that statement slightly nicer. Helps me also sort of compress. Now, if I were to do the same thing with R or HK, I get the same thing. I'm going to write them as well. For any F locally Riemann integrable and Newton integrable. Again, I need to assume both, okay? And for any 2 points, alpha and beta, well, the Riemann integral of f coincides with the Newton integral of f. You can state it for Lebesgue integrals. I'm not going to do that because I'd rather state it for HK integrals because we haven't sort of studied Lebesgue integral paradigm. I'd rather set it aside. The next 2 items are going to be in terms of HK integrals. And this is where HK integrals really shine. It says that Newton integrable implies HK integrable locally, and integrals coincide. HK is the same thing as Newton. Okay. Now, historically, for instance, Bourbaki integrals, I think, came after Riemann, but sort of, you might sort of read it this way. And so you might see, oh, you know, Newton knows how to integrate things according to him. And other people after him come and say, oh, look at this new integration. It works. And then he says, Newton, oh, but it is not the case that you can integrate any function that should be integrable according to me using your integration. So Newton says to Bourbaki, oh, that's not good enough. Then Newton says to Riemann, again, this is not good enough. You cannot just integrate all functions that I would want integrated using your bizarre Riemann sum whatever thing. So it's not good enough, it says. Riemann says. Same thing with Lebesgue too, but let's not worry about that. But finally, you see, you come to Henstock and Kurzweil, and Henstock-Kurzweil really impresses Newton. Finally, you have something, you have an integration theory that integrates whatever function Newton would think integrable. This is also, you know, proper. There are HK integral functions that are not Newton integrable, but so they can do more. But at the very least, using HK, you can integrate any function that has an antiderivative. So no hypotheses regarding f prime is needed. Insofar as a function is f prime, you can integrate it using HK. And, of course, integrals coincide. Okay? This was essentially the only reason why, the main reason why we discussed HK integrals. Yeah.
In Newton's life, does he realize that his method couldn't get the integral of all functions?
Well, I mean, I'm not quite sure. I'm sort of just coming up with the history, of course. Like, I haven't studied the actual history of this. It's sort of, I'm going back and I'm trying to relate to you. I'm just trying to tell you a story. Okay, this is not necessarily what happened. But the fact of the matter is, I would think that for Newton, even the idea of a function is somewhat dubious. He probably didn't use the idea of a function the way we used it. Because the people who actually formalized the idea of a function came after Newton. So that was the genius of Newton. Like, he could do math before calculus. You see, so he could do calculus before taking a class in calculus. So, and I'll tell you this too. It's like in our day, I've had the opportunity to, interact with some mathematicians like that too. It's like you talk to these people, and it's like they live in the future somehow. It's like I don't understand what they're doing, but what they say end up being correct. So there are people like Newton even today. Like very frustrating, if I say so myself. Anyone can read a textbook or a paper, or whatever, and understand things, but another big name is like Poincaré, like this. Okay, the final thing, I want to say something similar to this. I want to say if I have a function g that is differentiable, then g prime is HK integrable and blah, blah, blah. Differentiable, then g prime is HK log and for any alpha and beta in I, HK integral of g prime, again, I can just write it similar to this. HK integral from alpha to beta of g prime is g of beta minus g of alpha. Okay, that's a statement that I want to stick to. Any comments or questions? We might take part of tomorrow proving this as well. By the way, I should mention this too. Just because all of these are denoted in a similar fashion, because ultimately, when they work, they coincide as per the fundamental theorem of calculus. In order to really appreciate what is happening here, you should try to think about the definitions of each of these. Okay, so the Newton integrals are fairly straightforward. You just look at something like this. But if you were to look at this, so you need to take for any, so there has to be a number such that for any epsilon, there's a gauge such that some things happen, right? For Riemann integrals, you look at Darboux sums or whatever. For Bourbaki, you approximate your function using steps. It's like these left-hand sides, in a sense, are very different from each other and from Newton integral. Even though we sort of denote them pretty much the same way, the reason why is because, well, ultimately, the fundamental theorem of calculus should work. And so if different operations, no matter how complicated they are underneath, end up coinciding, well, their notation should be similar too. That's sort of like a general principle. Okay, so four is equivalent to 5, in fact. Okay? Because I'm saying if g is differentiable, g prime is, that means it is Newton integrable. And this just says Newton integrable implies hk. And so certainly, if I were to try to integrate g prime, which here is f, well, I'm just looking at the Newton integral. So 4 and 5 are the same. It's just that for whatever reason, I find 5 the easiest to remember. Integral of the derivative. Okay, that's how I remember it. Integral of derivative is, the function evaluated at the endpoints. 4 and 5 are equivalent, and certainly, since Riemann integrability implies hk integrability, and for Riemann integrable functions, Riemann integrals and hk integrals coincide, any one of these implies 3. Likewise, it implies 2. Likewise, it implies 1. So it suffices to show 5. I'll write it here. Five is equivalent to 4, which implies 3, implies 2, implies 1. So in principle, it suffices to prove only the last item here. But I thought what we would do is, well, we'll prove 5, and then ignoring the fact that 5 implies 3, we'll prove 3 using only Riemann integral theory, just to remind ourselves. Then again, ignoring the fact that 3 implies 2, we'll prove 2 using only Bourbaki integral theory. Okay? Sometimes it's good to sort of not take the logical sort of shortcuts, just to remind ourselves. And you're going to see the main idea is going to be this. With hk integrals, we're going to be essentially using the definition of differentiability. Okay? Nothing more. With 2 and 3, on the other hand, we're essentially going to be using mean value theorem. Mean value theorem, for instance, in this case, is going to help us sample any given specific partition, which then we'll be able to put into a Riemann sum to approximate this guy. That's what we're going to do. Here, for Bourbaki integrals, we're going to need to use step function approximation. Well, likewise, we're going to take our mean value theorem, and using it, we're going to come up with a step function that is close enough to this guy. That's going to be the main strategy. OK. I'll start with the proof of 5. Now you see everything is coming together. I'm assuming g is differentiable. I need to show that g prime is locally hk, and the candidate number is indeed the hk integral of g prime. So I'll write it like this. Suppose g is differentiable. I'm going to slow down here a little bit and try to be as explicit as possible in the proofs of these, because this is the main course of this course. Suppose g is differentiable. Here, alpha and beta are arbitrary, but without loss of generality, I can assume that alpha is to the left of beta. Okay? Because ultimately, this is going to turn into an unsigned integral once I sort of figure out which one is to the left, which one is to the right. Without loss of generality, we can assume that alpha is a number strictly less than beta. Okay? We claim that g prime is integrable, and its integral is the candidate. Let's remind ourselves. I want to open this up, okay? I want to use the epsilons and whatever. So this is going to be the candidate integral. I need to say this. For any epsilon, there is a gauge such that for any sampled partition that is delta fine, the associated Riemann sum of g prime is epsilon close to the target. That was the definition of HK integrability. Okay, there's a delta. Now, I'm not integrating on the whole interval I, I'm integrating on alpha beta. Okay, so this gauge is going to be on alpha beta only, such that for any sampled partition, okay, of alpha beta, what do I need to say? I need to say if PS is delta fine, then the associated Riemann sum is within an epsilon of the target. Delta fine implies Riemann sum of G prime relative to PS is close to this point, this number. I just opened up the definition of what it means for G prime to be HK integrable on this closed and bounded interval, and its integral being this. As you're trying to prove things, it's often a good idea, at least initially, to sort of expand and remind yourself. Start talking to yourself and sort of rewrite what you're trying to prove. Now this is somewhat more actionable. You see? Okay. So ultimately then, I'm going to take an epsilon. I need to construct a certain gauge. Okay? And things are going to happen, and ultimately, this Riemann sum for G prime is going to be, I want it to be close to this. Okay. Well, what is one of the methods of proof? Well, we look back at things that we haven't used so far. Well, the only thing that we haven't used is the only thing that we were given, namely that G is differentiable. So somehow using that, I want to come up with a gauge. Okay? So this is the target. This is what we're trying to do. Put that aside. G is differentiable. Now, I had given as an exercise that you can state differentiability in terms of gauges. Now, I think I'm going to do it just to remind ourselves. What do we have? Because here in the statement I'm trying to prove, I have an epsilon. I'm going to use a different letter for the so-called epsilon for differentiability. I'm going to use, say, eta. So what does it mean for G to be differentiable? It means it is differentiable at every point. In particular, it's differentiable on alpha beta. For any x star and for any eta positive, there is a delta. It's not a gauge. This delta is not the same delta as this. There's a number such that for any x in Well, I guess I can write it as I here for now. For any x in I, what do I need to say? I need to say that if x is delta close to x star, then, well, I have this. F of x minus f of x star plus f prime of x star times x minus x star is bounded by eta times x minus x star in absolute value. Right, so if I were to take this, divide everything, I have the sort of rise over run here. Here I have f prime. Instead of writing it like that, I just sent the denominator to the other side. Okay? Okay. Now, from this, somehow I want to come up with some sort of a gauge. Here's what I'm going to do. This is sort of the solution to that exercise. Rephrasing differentiability in terms of gauges. Plus for any x star in I and for any eta in positive numbers, I'm going to do something funny. Okay? I'm going to look at the set of all those positive numbers delta such that the rest holds. Capital delta, this set, this is going to be the set of all those deltas such that the rest is true. Implies, well, I'll just put a star here. So this statement is true. By virtue of the fact that G is differentiable, this set that depends on x star and eta is a non-empty set of real numbers. There's at least one delta like this. Okay? Saying for any x star and eta, there's a delta. Okay. That delta is an element here. It's a set of real numbers bounded from below. In particular, if I were to look at the sup of this, well, it cannot be negative infinity. It could be infinity, because it could be, in principle, unbounded, this set. But what I can do is, I can define delta sub eta of x star to be 1/2 min of 1 and the sup of this set. Okay. That certainly is a positive number now. Okay. But then what I can say is, this depends on x star, and this defines, in fact, a gauge on alpha beta. If I were to choose x star to be some point in alpha beta, for any eta, I have one gauge on alpha beta. It's a gauge on the whole interval if you want, but this is what we're going to use. Okay. So somehow, we're running out of time, somehow I'm going to use these, and sort of using these, I'm going to be able to get this gauge in the HK integral definition. Okay. We're going to continue tomorrow. Thank you. All right, let's start. Good morning. Attend this again. So we're going to keep working on this first fundamental theorem of calculus. I wrote all the statements again. Remember yesterday we had started talking about the proof of 5. And I told you that 4 is equivalent to 5, which then implies 3, which in turn implies 2, and any one of them implies 1. So what we're going to do is, first I'm going to give the proof of 5, then we're going to discard that proof, and the fact that that implies this, prove 3 using only Riemann integral theory, then discard the proof of this, and prove 2 using only Bourbaki integral theory. Okay, just so that we have a summary and review of all of these different integration theories that we've discussed so far. You can also state things for Lebesgue integrable stuff. Remember, for us, a function was locally Lebesgue integrable if and only if it is HK integrable locally and its absolute value function also. This was a definition that we used for local Lebesgue integrability. Now, those of you who are going to take more advanced analysis classes, you're going to learn local Lebesgue integrability starting from this Lebesgue paradigm of integration. Remember, there were two distinct, at the very least, two distinct paradigms for integration. And all of these we're doing are within the context of Riemann integration paradigm. But even though there are these two integration paradigms, we can talk about Riemann integrability from the Lebesgue paradigm and vice versa. Okay? So you're going to spend a lot of time on this Lebesgue integrability, those of you who are going to take more advanced classes, although the definition you're going to use is not going to refer to HK integrals, technically, probably. Because this Lebesgue paradigm, which people often use to define this Lebesgue integrability, is completely different. You don't really use the gauges and stuff like that. The flavor is very different, so we're going to sort of set that aside. OK. So for instance, here what I can say immediately is, if a function is locally HK integrable and taking only non-negative values, it's also automatically locally Lebesgue integrable. Because if f of x is always non-negative, this is equal to itself. So this is equal to f in absolute value. So there's no distinction. We'll see the effect of requiring that f in absolute value is also integrable later. So this example, remember, we had so we had x squared cosine of 1 over x squared, and then we took the derivative of this. Okay. When you take the derivative of this, this function is unbounded, and therefore it is not Riemann integrable on any interval containing 0. I kind of mentioned that this is also not Lebesgue integrable, because the fact of the matter is, when you do this differentiation, this function, it has a sign whatever, even though it blows up like this. So somehow, if you don't take the absolute value, the positive contributions somehow balance out the negative contributions, and so you get to integrate this according to HK. Okay? But if you were to take the absolute value of this, which corresponds to just looking at the parts of the oscillations that are dipping down and sort of flipping them, then positive and negative contributions don't cancel out. And then once you try to take the integral of the absolute value of this derivative, the integral blows up, which is why this derivative function is not Lebesgue integrable, even though it is HK integrable. Okay. So later on, after we're done with Taylor approximation, we're going to start looking into series, infinite sums of numbers, say. And there too, we're going to have a similar dichotomy. There are going to be certain series that converge, we're going to say, absolutely. And there are going to be some that converge conditionally. And so Lebesgue integrables correspond to absolutely convergent series, okay? So this is, for instance, something like 2 to the minus n. On the other hand, hk correspond to something called conditionally convergent series. An example for this is something like this, for instance. Minus 1 to the n. So minus 1 to the n divided by n. This is a convergent series. We're going to see later. One of the things that we will probably discuss is what is called the alternating series test. It says that if you have a series like this, and if the terms that you're adding over converge to 0, then once you have this alternating business, minus 1, 1, minus 1, 1 alternating, then this is going to converge. But certainly if you take this, this is nothing but the sum of reciprocals of integers, and this blows up. This is infinity. It doesn't converge. So hk is something like this, okay? Hk integrable functions are functions that you can integrate, but in principle, if you take the absolute value of the function, then the integral might blow up. Those functions that you can integrate relative to hk, and even when you take the absolute value within the integral still converges, that is Lebesgue integrable. That's why Lebesgue integrable functions are more restrictive. We're going to see this dichotomy later again. Okay. Any comments or questions about what I said so far? Like I said, I want to take my time because this is sort of important. This was what we were building up to. As far as I'm concerned, this class and the next class as well, the 30 to 20, it's always sort of leading up to the fundamental theorems of calculus. That's why we've been defining all of these things rigorously and stuff. Okay. So let me write it again. I'm going to remind you everything we wrote so far. So I'll start with the proof of 5. Okay. So I'm supposing I have some function that is differentiable, g. I want to show that g prime automatically is hk integrable on any closed and bounded interval, subinterval of I. And indeed, the hk integral of the same function matches with the usual suspect. That is the Riemann integral. Sorry, the Newton integral. So I'll take 2 points without loss of generality. I can assume that alpha is to the left of beta. Right? Because if alpha were equal to beta, then all the integrals are going to be 0 by definition, so I can just discard that. Well, if alpha is to the right of beta, then I can just rename alpha beta and beta alpha, so that's all good. And I have a function that is differentiable. Since g is differentiable, what did we do last time? I just expanded what it means for g to be differentiable. In order for a function to be differentiable, it has to be differentiable at every single point. So I can write it like so. For any x in I, And for any, I think I used eta, positive, the set capital delta, that depends on these two choices, defined as the set of all those positive numbers delta such that, well, differentiability holds for any x in I, if x is delta close to x star, then the associated approximation works. And I think yesterday when I was writing this, I mistakenly wrote f instead of g. I should have written g, of course. So g of x minus g of x star plus g prime of x star. Okay. I'll write it here. G of x minus g of x star plus g prime of x star. So I should be multiplying this by h, which is supposed to be the difference. So I need to write here x minus x star. Okay, so here it's like this. So what I'm saying here is, here's my original function, here's the affine approximation. First order polynomial that approximates this. Okay, this is bounded by eta times x minus x star in absolute value. So set of all those deltas such that this works. Differentiability says this set is non-empty. Hence, if I were to look at its sup, it could be infinity, it could be a non-negative number, but it cannot be minus infinity. And in fact, what you can say is this, okay? There's at least one delta, lowercase delta, and this uppercase delta, such that this works. But then, if you were to shrink your delta, that delta would still work for differentiability, which means I can in fact say that, I'll write it here, this capital delta is a fairly nice set, in fact. It's pretty much an integrable in and of itself. The sup could be infinite. That's why I need to sort of do something about it to get a gauge. But then what I can do is define then delta sub eta of x star to be 1/2 of min of 1 and the sup of this set. Okay. The specific expression of this doesn't matter that much. It's just a small number that is well defined that I can use like this. And so you see for each eta, I have one function, delta sub eta, that depends on x star. In principle, this is a gauge on the whole interval, but I'm going to use it only on the closed and bounded interval alpha to beta. So I can just say delta sub eta is a gauge on this closed and bounded interval. Okay, remember this was my notation for the collection of all gauges on this closed and bounded interval. And what is a gauge? It's nothing but a function that takes positive values. Okay. So you might call this the differentiability gauge associated to G, if you want. So this is the gauge that controls the differentiability, the approximation property that defines differentiability for G. Any comments or questions so far? Yes?
That triangle
Yes.
with x star and eta,
Yes.
I can understand the set builder notation, but that notation is what?
Well, I'm saying define capital delta of x star eta.
That's their argument?
You can think of it that way too if you want. You can think of capital delta as a function. You can think of it like this if you want. You don't have to, but you can.
So that's a partition?
No, this is the space of all subsets. Power set.
Oh, how is it?
Yes. People don't like writing these things explicitly, but you can if you want. It's perfectly, my notation is perfectly compatible with what I defined in week 1, even though it may not look like it.
So it's a tuple
What is a tuple?
or tuple?
This?
A set.
Yes. Yeah, it takes 2 inputs, the base point and what you want your error what you want your error here. And based on that, you look at this condition, the set of all those. So you want a delta such that this whole thing works. It's kind of rather convoluted to define something like this way, but within our logical system, it's a perfectly valid mathematical object.
So you have a set called delta,
Yes.
where you annex it with 2 numbers.
Yes.
And this set is a number set?
It's a set of numbers, yes. Because instead of all those deltas, in the definition of differentiability, delta is a positive number. So I'm cutting out a certain collection of positive numbers.
If you wipe out those x star and eta,
Okay?
it's still there. Definition of delta.
Well, yes, I mean, you don't need to write it. But I guess I'm trying to be explicit about the fact that this delta, this capital delta, this set, depends on these 2 choices. If I were to choose a different base point, choose a different error margin, the delta would change in principle. Okay? Yeah, so maybe it's a good point. Let's try to make sense of this. Right, so you don't, like I said, you don't need to write it, but I'm being explicit here. Because when I say, oh, I'm just going to look at the soup of this capital delta that depends on these 2 points, it's clear that the end result is going to depend on eta and x star also. But for instance, imagine this situation. Right, so x star, this argument is about the base point of where you're taking the derivative. And eta is how much of an error margin you want in the approximation. So that means that if g is a function that is very steep near x star, then capital delta should be a smaller set. Okay, because you would need more control to be able to get the same error margin. Okay. Yeah, so you can say things like this. If eta 1 is less than eta 2, you can try to compare the 2 capital deltas. Okay, I have 2 sets associated to 2 error margins. But if you can, if a delta works like that for eta 1, it's also going to work for eta 2, which means that this is a subset of the other one. Okay, so you can do things like this. And say this is x dagger and x star. say your function is something like this. Okay. In fact, it's flat here. Around x star, it is flat, and then here it goes like this. Okay. This is your g. So what is this eta ultimately? It tells you, how to say, one way to think about it is, so the smaller the eta, the better, the easier you get to approximate g near x star using a function whose graph is a line. Okay? So maybe I should have put something that has like more curvature like this. So here, I guess what I'm trying to say is, here, for instance, at this base point, the approximation, the linear approximation to g near x star, given by this function over here, fits really well to the graph of g. Okay? So this allows you to be able to take eta very small. But here, even though this function is still differentiable, so you have a linear approximation, you see the graph of the linear approximation doesn't fit as well as this guy. So you start comparing the graph of g and the graph of the linear approximation. And you say, OK, the graph of the linear approximation matches on the nose with the graph of g at x star. Now you start taking nearby values. Okay? You keep comparing the graph of g and the graph of the approximation. Okay? In principle, the farther away you go from this x star, the more the error should grow. Okay? In this part, because the graph of g is flat, the error is not going to grow as fast, for instance, compared to the error that you would start obtaining if you were to start sort of looking farther and farther away from x dagger.
So it's related to the slope of the tangent line?
Probably it's better to call it curvature.
Tangent curve.
Yes. So up to first order, linear approximations are going to work nice. But a differentiable function, in principle, have higher order terms. Imagine a parabola. Okay, we're going to talk about approximating that next week with Taylor approximation. Okay. What you see is like, just by using basic logic and transitioning between logical statements and sets, you can really get very quantitative about a lot of things. So, okay. Any other questions about this? Okay, let's continue. In any event, we have a family of gauges, if you want, because for each eta, I have a different gauge. Okay. Now, what do I need to show? I need to show that G is G prime is HK integrable on alpha beta. Okay. I'll write it here again. I want to show that G prime is HK on alpha beta, taking real values. what does that mean? Expanding, let's remind ourselves, for any epsilon, there is a gauge on the set such that for any sampled partition of alpha beta, if that sampled partition is fine relative to the gauge you chose, you were able to construct, the corresponding Riemann sum is arbitrarily close, is epsilon close to the target. And the integral is g of beta minus g of alpha. So in the definition of HK integrability with integral r star, this is going to be the specified value. Okay? I have the candidate. So I can write it like this. For any epsilon positive, there is a delta, which is a gauge on alpha beta, such that for any sampled partition of alpha beta, if the sample partition is delta fine, then the associated Riemann sum of G prime is within an epsilon of r star, this G of beta minus G of alpha. Okay. Expand it out, that's what I'm trying to do. That's just a definition of HK integrability. Now, as usual, I want to start from the end. Okay? I'm just going to take an arbitrary sampled partition PS, and I'm going to try to control this distance. And then I'm going to try to figure out how to engineer a delta that would fit here based on this delta, of course. That's the reason why I sort of expanded this. Okay? So, I take a sampled partition of alpha beta. Now, in this case, usually I often thought of sampled partitions in terms of the pixels, the subintervals included in it. But in this case, because we're going to do some sort of a calculation, it's better to think about the cut points. I'll write it like this. Okay. P has to be of this form. Now, one thing I can do is, without loss of generality, I can say that each of these pixels has positive length. Otherwise, I'll just like bunch a bunch of them together. And x0, of course, is going to be the left endpoint. Yeah. And of course, instead of writing S of this interval, I'm just going to say SI. And so S1 is some number between x1 and x0 and x1. And then S2 is like this, and so on. Okay. I can think of this sampled partition merely as this list. Has more indices, fine, nastier to write down compared to this more sort of abstract notation, but it's going to come in handy in our case. Okay. Now, I start from the end. I'm going to start with what I'm trying to control. Okay, there's this. Minus r star is this. Well, I'll try to, okay, fine. This is ultimately what I'm trying to control. This I'm just going to expand using this. Okay, I know what this Riemann sum is. This is the sum of I from 1 to n, right? G prime at Si times the length of the ith pixel. And in this case, it's just going to be xi minus xi minus 1. This is associated Riemann sum. As you see, it's, in my opinion, it's more nasty than adding over the pixels. Yeah, like indices and stuff. I always get confused. Okay, so this is the Riemann sum. Now I want to do something about this. Okay, and in fact, the idea that I always have in mind when it comes to this is also this fundamental theorem of calculus that you've encountered in the context of discrete derivatives a while ago, which is also the same idea as this Newton cradle for some reason, in my mind at least. So you have this thing, you have a bunch of beads like this that are like hanging. And so you take one of these, okay, you let it fall, hits this guy, and then once this one hits this way, the only bead that moves is this one. This is one of these like executive toys. Of course, this just tells you F equals ma whatever. But somehow I want to say something. I want to say that this expression is in fact a mathematical sort of metaphor for what is happening here, or the other way around. Okay, so for instance, how can I get g of beta? Well, if I were to do this, okay, g of xi, okay, minus I from 1 to n, g of xi minus 1. Okay. This is sort of like a telescoping sum. That's also what you did in this discrete fundamental theorem of calculus. What is happening, you see indices kind of make it hard to see what is happening, but I'll try to draw it. Here. This was the big interval I. I sectioned off a closed and bounded subinterval here. I then partitioned it. Okay. I said, oh, this is going to be x0, this is going to be xn. Okay, this is x1, x2, whatever. And then I also have samples. This is s1, s2, whatever. So far, I haven't used the samples, but you see, this basically tells me something similar to this Newton cradle. It says, give some potential energy to the bead on the left-hand side, let it go, and you're going to see the output as the potential energy transferring completely to the endpoint. And so if you were to look at this, okay, that corresponds to adding all of these. So these are giving you positive contributions. But then I'm subtracting from it the other sum, which runs over the left endpoints. Okay? I say that's a negative, that's a negative, that's a negative, that's a negative. And so the ultimate, so at the end, when I do this summation, well, all I'm going to be left with is one positive contribution coming from the right-hand side and one negative contribution coming from the left-hand side. Everything else is going to cancel. Yes? That's the idea here. Even though from a mathematical point of view, perhaps it looks kind of bizarre because I'm sort of writing it in a more bizarre fashion. That's sort of the idea I'm imagining, which kind of reminds me of this too. Okay. Okay. I'll do one more thing. I want to include into this picture the value of g at sample points as well. So I'm going to subtract, say, from this g of si's and add to this g of si's also. Okay, I'm leaving the Riemann sum part minus. And in fact, I'll distribute the minuses as well. Yeah, put a plus here. Should I distribute it? I'll leave it for now. Okay, like so. Minus okay. So from here to there, oh, this was like this. All I did was I subtracted g of si's from this sum, but in order for the equality to hold, I need to add the same things here. But because there's a minus here, I need to put a minus here. Okay? This is nothing but basic algebra. I'm not doing anything about calculus. Okay. But of course, now the point is I'm summing over the same thing, so I can just consolidate everything. And in fact, I can put the absolute value inside also. I think I'll erase this. So from start, consolidate. I'm going to erase this picture also. Consolidate the finite sums and then distribute absolute values using triangular inequality. Now I have an upper bound on that. But at the same time, I'm going to split this too. So maybe I'll do this in 2 steps. Okay, fine. Okay, plus, minus, I guess. Minus I from 1 to n, g prime of si, xi minus 1 minus si. Just like I injected g of si's from here to there, I'm doing the same thing here. So I have this, then I have 2 more things. G of xi minus g of si And I think now it's OK for me to distribute at least this minus plus sum over all i's of g of xi minus 1 minus g of si. OK. That's nice. So how I'm going to collect these terms is based on the type of differentiability gauge that I already had. So at this point, I know that I can control expressions of this form if I get to use this gauge. Okay. Therefore, what I'm going to do is I'm going to collect this with this and this with this. Okay. And at this point, I can consolidate the sums and distribute using triangular. Yeah, I'll continue from here. So I'm going to collect this with this. Okay. This is this term, then minus this term. So plus g of si. Like so. And then I have one more term, one more summation. This and this. Like so, minus this. Minus with a plus. Like this. Okay. By triangular. And so for eta, a positive number, if I were to take my sampled partition to be delta sub eta fine, and in a previous problem set, you showed that for any gauge, there's at least one sampled partition that is delta fine relative to it, then I have a good control over this. Because by virtue of the fact that I define this delta sub eta in tandem with the differentiability property, you see this expression is exactly this for x star equals si. And the fact that the hypothesis that ps is delta sub eta fine would tell me that xi is going to be within a delta sub eta of si and so on. Okay? I was worried for a second that this wasn't going to end today, but I think we're seeing the light at the end of the tunnel. Thus, for eta arbitrary, if ps is delta sub eta fine, then the thing I'm trying to control, the associated Riemann sum of g prime and the usual suspect, is upper bounded by what? So we started from here, boop, and then you go over there, and then you go over there. This thing is bounded by this, but by virtue of the fact that ps is delta fine, since xi is one of the endpoints, of the pixel that contains Si, well, this allows me to say that this is bounded by eta times xi minus si. In absolute value. And I have the same thing here. Xi minus 1 minus si. Okay. I can take the etas out. And using the fact that si is in between xi minus 1 and xi, I can get rid of the absolute values as well. This is eta times I from 1 to n. This is just xi minus si without the absolute values, because this is always non-negative. And if I were to flip the orders of these, this is also going to be always non-negative. So I can just consolidate everything as well. Plus si minus xi minus 1, this whole thing. But then these two cancel out. And ultimately, you get eta times the length of the interval alpha beta. And so for any eta positive, I have a gauge, delta sub eta, such that for any sampled partition, if the sampled partition is delta sub eta fine, then the associated Riemann sum of G prime is at most this far away from the usual target, the usual suspect. But then if that is the case, for epsilon positive, I can choose eta to be epsilon divided by this length, and I would be done. Choose eta to be epsilon by the length of the interval, which then would allow you to replace this whole thing by epsilon. So ultimately, I was able to show for any epsilon, there is a gauge. So I'll write it here. This specific gauge, which is epsilon divided by the length of the interval, works for HK integrability. That's what I was trying to say. Okay. Now, there's also like a different style where you start with an epsilon, and then instead of looking at this whole thing, you do all this stuff with eta, the fixed value that you need to use so that the thing ultimately works. These are different styles. I like to sort of separate different parts of the estimates and then sort of connect them at the very end. I don't like sort of carrying epsilons around. That's a stylistic choice. In my style, it's also rather straightforward. After you do all this work, watch with which epsilon you should be sort of using. You start with an epsilon, and then if you use epsilon divided by the length, then once the dust settles, you have an upper bound as epsilon. It becomes clear if you do it like I do. Otherwise, it gets slightly more messy, the approximations and stuff, but it's to your taste. Okay. So that's the end. That's the end of the proof of 5. So technically, we're done with the proof of the first fundamental theorem. But like I said, we're going to ignore this proof and do the same proof for Riemann integrals and Bourbaki integrals also, just as a reminder of these different integration theories, even though in principle, this proof implies the other ones as well. Okay, and that we're going to do on Friday. Good? All right, thank you. I'll see you on Friday then. All right, let's start. Good morning. I'm going to take attendance again. So I plan to finish the proof of the first fundamental theorem today, and then we're going to transition to the second fundamental theorem, which is when you have this the other way around. First you take an integral and then a derivative. So technically we're actually done with the proof because we proved 5. That's equivalent to 4, and everything else is implied by these. But what we're going to do, just so that we understand all of these different integration theories, is that now ignoring the proof that we had for 5, we're going to try to prove 3 using only items from Riemann integration theory. And then we're going to discard that proof again, because a proof of 3 also implies a proof of 2. We're going to discard the proof of 3. We're going to try to prove 2 using only Bourbaki integration theory, just so that we have an idea as to how these different integration theories work and what are sort of commonalities in the arguments and stuff. So one of the arguments that we used, for instance, in the proof of 5 was this Newton-Cradle idea, namely this Newton integral, antiderivative evaluated at the endpoints and subtracted. Well, we were able to write this as sort of like the consequence of a telescoping sum. And so from a physical point of view, that kind of is similar to this idea of the Newton cradle, which I realize it's easier to first draw the beads and then the little lines, or pieces of string. So we use this idea essentially to open this up and then do some rearrangements. We're going to see that the same idea is going to show up in 3 and 2, but we're going to sort of turn that into a mathematical idea in a different sense, depending on these different integration theories. So I'm not going to restate everything again. As usual, the standing assumption is that I is an open and non-empty interval, and we had proved 4 and 5. I want to just focus on 3. Before going into that, I just want to give you a recap on this proof of 5 also, just to compare the different strategies. So you see in 5, we essentially used the definition of G being differentiable. Okay? And so given that G is differentiable, we were able to come up with a differentiability gauge, or a family of differentiability gauges. For any eta positive, there is one gauge, delta sub eta, such that for any x, the rough idea was this. Delta sub eta of x is very small, is when the graph of G bends a lot near x star. If the graph of G is like a line near x star, then the associated gauge at x star could be very large in principle. When it is small is when G bends quite a bit. Okay? In other words, next week we're going to sort of transition to higher order terms as well. That means that G has higher order terms that contribute quite a bit. Okay? But then we took this gauge coming from differentiability and just plugged it into the definition of HK derivatives, or HK integrals. And so given this family of gauges, if PS is a sampled partition that is delta fine, well, one of the sampled points is going to be near x star. I'm kind of imagining that this pixel in curly P includes this x star, which then tells you delta fineness requires that the pixel P that contains this sample should be small. That's what it means for PS to be delta fine. Okay? Which ultimately means that the pixel should have length very close to 0. Okay? So this was basically the idea of the proof for 5. We said if the graph of G bends quite a bit, well, there's going to be sort of like a small rectangle coming from it to approximate the integral. Well, I want the base of that to be very small so that the discrepancy is small. Okay, this was the rough idea. We use this together with this Newton cradle idea to get the proof of 5. Okay. Any comments or questions about this so far? Okay. So discard the proof of this. Let's now try to figure out a proof of 3. Now, again, just to reiterate, what is the sort of major improvement from 3 to 4, let's say? You see, in 3, we have to assume that the function that we start with is both Riemann integrable and Newton integrable. In 4, all you need to assume, or in 5, all you need to assume is that the function that you start with is Newton integrable. Newton integrability automatically implies HK integrability. Meaning, if you have a function that is differentiable, you can definitely integrate g prime according to HK. But it might be the case that you have some function that is a derivative of some other function that you cannot integrate according to Riemann. I had given you examples for this. So that's the main sort of difference between this side of the theorem and this side. OK. And the same thing holds for Lebesgue integration too. Lebesgue integration, it would be on this side also. So HK is even better than Lebesgue integrals as well. OK, so split it like this. Proof of 3, ignoring the proof of 5. I don't recall there being a bell. I feel like this is new. Interesting. OK. So this time, I forget everything about this HK integrals and so on. And I'm assuming I'm starting with a function that is both locally Riemann integrable and Newton integrable. As before, I'm just going to take a function like that. I'm going to abbreviate it like this. Alpha, beta be in I, and alpha be to the left of beta without loss of generality. Okay. This is so that I don't need to worry about these plus and minus signs. I'm just going to look at unsigned integrals ultimately. OK. And again, to reiterate, when we were proving 5, I didn't assume that g prime was HK integrable. I proved it was HK integrable. Here, I need to assume that the thing I'm trying to integrate is integrable, really, relative to the integration theory I'm considering. OK. Let's see. OK, I'll start with a partition of alpha beta. Just like before, I'm going to assume that the length of each pixel in my partition is positive. And therefore, I get to think of P in terms of its cut points, which is a strictly increasing list of finitely many points. So x0, x1, x1, x2. This is not strictly necessary. It just makes things, calculations slightly easier to write down. OK, it's like this. Without loss of generality, this means alpha is equal to x0. It's a strictly, it is some number that is strictly less than x1, which itself is strictly less than x2, and so on. Finally, I have xn, and I want this to be beta, of course. OK. Now, I want to say something about the associated Riemann sum. So first of all, I'm going to choose a sampling function, of course, adapted to P. But you see, this time, instead of directly using the definition of differentiability in terms of gauges, what we're going to do is we're going to use mean value theorem. As lowercase f is Newton integrable, there is some function, capital F, by definition, such that capital F prime equals lowercase f, by the assumption that lowercase f is Newton integrable. By the assumption that lowercase f is Newton integrable. Okay. Now, whenever I have a bunch of distinct points, the first thing I should think of is the mean value theorem. I'm going to apply mean value theorem to f. On each element of curly P, well, I have this. For any I from 1 to n, right, there is some point S sub I, let's say, strictly between the endpoints, x sub I minus 1, x sub I, open, such that the rise over run is f prime evaluated at this point. Okay. Mean value theorem applied to each of these intervals. But then I can rearrange this. Capital F prime is the same thing as lowercase f, and in the denominator, I'm seeing nothing but the length of the pixel. Okay. This is really nice because I know that if I were to look at the sums of all these terms, that's going to give me a Riemann sum according to this partition with this sampling function, okay, on this side. On this side, if I add over all i's, I have the Newton cradle idea, and the sum of these is going to give me f of beta minus f of alpha. Okay, so I'll write it like this. So S, maybe I'll write it like this. S star, that goes from curly P into alpha beta, where you take xi minus 1 xi, this is one of the elements of curly P, into this specific point. You see, there could be multiple such as a consequence of mean value theorem. All I need is one sampling function, is a sampling function associated or adapted to curly P. And the Riemann sum of f relative to Ps is precisely the sum of these. S star, I should say, is sum i from 1 to n of these terms. Okay. Now, what does this say? Ultimately, this tells me that for any partition curly P of alpha beta, there is some sampling function such that the associated Riemann sum is this number. But also, by virtue of the fact that this is equal to this, I can keep I can substitute instead of this, Newton cradle. So I'm going to have f of x1 all the way up to f of xn, which is f of beta, minus f of 0, which is f of x0, which is f of alpha, and then minus f of x1 and so on. So Newton cradle gives me this. Okay. Consequently, for any partition, there is a sampling function such that the associated Riemann sum is the Newton integral. Write it here. I think I'm going to erase this. I want to keep this side. For any partition, there is a sampling function adapted to this partition such that the Riemann sum is the Newton integral. Okay, so this is the same thing as this. This doesn't depend on, maybe I should write it like that actually. It's better notation. Okay. Now, so far, the only thing we used was, in fact, the assumption that f is Newton integrable. I haven't used the fact that f is Riemann integrable. If I use that, now I can say something more. Okay. So let epsilon be positive. Okay, so in this third item, we are assuming that f is Riemann integrable on alpha beta. That is to say, the Riemann integral exists. So both sides of this equation exists. Here, I'm assuming that they exist, but I'm trying to show that they are the same number. Then there is a delta, positive, such that for any sampling function, for any sampled partition, or I can write it like this actually, for any partition, if the mesh of the partition is bounded by delta, then this expression, oh, I should write it like this. Is bounded by epsilon for any sampling function associated to p. So I can just write it like this, soup over all sampling functions. Well, but then what I can do is I can look at the difference between the two, compare the Riemann integral and the Newton integral. Inject one Riemann sum like this using whatever partition you have. Yeah. like so. What do I want to do here? Ah, okay. So I should write perhaps here, for any PS, the difference between the Riemann sum and the Newton sum is upper bounded by this, by the triangular inequality. Now, if I were to take the sup of this summand over all sampling functions associated to P, this can only increase. But then over that, I'm going to take an inf. Okay. So this is going to be like so. Better. Oh, that's an R. I'm taking the sup of only this summand. This other side I leave as is. Okay. So consequently, for any partition, the difference between the Riemann sum and the Newton sum is upper bounded by the sup of this expression over all sampling functions adapted to P, and this guy for an arbitrary S, which means if I were to take the inf of this over all sampling functions, I still get an upper bound. So to be clear, I can write it like so. This like so, plus inf of this expression okay, that's nice, because we had shown that for any partition of alpha beta, there is one sampling function where this is equal to this, which means this inf is 0. By dagger, this is 0. And well, by Riemann integrability, I can make this as small as I want, which means as this doesn't depend on the partition, whatever this distance is bounded from above by an arbitrarily small number, which means it has to be 0. Double dagger says okay, so I have two numbers, Riemann integral and the Newton integral, whose distance is upper bounded by an arbitrarily small number. That means they have to be the same number. Alternatively, you can sort of rephrase this proof by choosing first. So if you do it the other way around, you would first choose an epsilon. Then that would tell you that there is some delta such that for any partition, if the mesh of the partition is bounded by delta, then for any sampling function associated to this partition, the Riemann sum is within an epsilon of the Riemann integral. Then you would expand and you would apply the mean value theorem on any antiderivative associated to this or according to this partition, get this expression, and you can sort of write it that way as well. It's the same idea. Yes?
Can you explain why you take the in?
Yeah. So broadly speaking, this is a strategy I'm using here. Let me see. Let me put it this way first. What I'm trying to do ultimately, is to show that this is 0. Okay, because I'm saying that this number is the same number as this number. Okay, instead of showing that this number is the same number as this number, I'm going to show that their distance is 0. Okay, I'm looking at the distance. Now the point here is nothing changes here if I were to change a partition, whatever. Once I fix my function f and the endpoints alpha and beta, this is a well-defined number that I cannot move. Okay, this is stationary. So I have on the left-hand side some constant. Okay. Now I figure out somehow that there's an upper bound to this in terms of certain variables. Okay. So let's say the left-hand side is, I'll leave the left-hand side as left-hand side. How do I want to say this? Say it's like this. Left-hand side is a constant. I'm saying there are two functions that depend on the same parameter. In this case, it depends on two parameters, but never mind. That depend on the same parameter, such that there's some upper bounds to the left-hand side. Now, even though they depend on the same parameter, I can decide to take the sup of one of these. Okay? Now I have this. Okay? Because sup of A upper bounds this. But then, if it is a case that for any x, left-hand side is bounded by this, consequently by this, as I vary x, left-hand side minus the sup should be a lower bound for b of x. Right? So send this to the other side. But then if that is the case, whatever this expression is, it's a lower bound on b of x, which bounds from the left. Consequently, the inf of this, it exists, and it has to upper bound this, because inf is the best lower bound. And then putting this on this side. I have this. That's ultimately what I used.
And that inf you referred to here?
Yes. If I were to fix my partition, I have the set of sampling functions adapted to it. For each sampling function, I have one Riemann sum. On the other hand, this is constant. Okay? So if I were to look at the distance between these two, for fixed p, this distance would be a function on the sampling function. Okay? As I vary the sampling function, I can see, does this increase or decrease, whatever. I'll write it here. So, red dagger says this. So first, look at this. For each fixed partition, consider, so this b of x is going to be this. It's going to be b of s. Okay. This is a non-negative function. Right? At least it can be 0. It cannot be a negative number because I'm taking the absolute value. But I'm telling you by dagger that it attains its minimum. So this inf is 0.
Although you switch between a function of x to be a function of x.
Yeah, sure. Yes. But I didn't tell you where x was coming from. I didn't tell you x is a number. X is coming from a set. In this case, it's a set of all sampling functions adapted to p. And why did I decide to take the sup of this side and the inf of this side? Because by the assumption that f is Riemann integrable, I knew that I could control the sup of this by some number that is arbitrarily small. And by Newton integrability, I knew that I could control the inf of this. Okay? That's the idea. Any other comments or questions about this? Again, like you don't need to write it like this. You can just start with taking an epsilon and then sort of keep tracking it down. My style, generally speaking, is I don't like keeping epsilons and I don't like sort of carrying them around. I like broad estimates, and I like sort of writing estimates down. And then at the last step, I want to sort of, I like bounding by epsilons and stuff. That's kind of my style. Because as far as I'm concerned, keeping track of inequalities like this, it makes more sense to me. It's like it really tells you, oh, you see, this is a side coming from Riemann integration. This is a side coming from the Newton integration and so on. I just like it like that. You don't have to write it like this. Okay. So that's the proof of 3. Okay. So let's ignore that we proved 3. Let's try to prove 2. Ultimately, we're going to use mean value theorem again. But this time, let's remind ourselves, for Bourbaki integration, what was the idea? The idea was, well, we need to approximate this f using a step function this time, or a sequence of steps, whatever. Okay. I think I'm going to leave this. I'm going to keep this. I know we're sort of slightly behind schedule, but as this is the, one of the most important theorems that we're supposed to learn in this course, I'm just taking my time expanding on things. And I hope you also see how everything that we learned so far sort of come together as well. Soup, inf, whatever, all these we're using, and Riemann integration, mean value theorem. You see, all of these different components start sort of interacting with each other. Okay. Proof of 2, ignoring the proof of 3 and 5. Proofs of 3 and 5. Okay. So, as before, I'm going to take a function according to the hypotheses. Just like with Riemann integration, I need to assume that f is both Newton integrable, it has an antiderivative, and also the Bourbaki integral exists. Okay? Let f be locally Bourbaki integrable and Newton integrable simultaneously. I'll take 2 points, alpha and beta. In I, alpha to the left of beta without loss of generality. Okay? Now, I can try starting with a step function on alpha beta and sort of try to do something with it. But in a previous problem set, you saw how instead of just thinking about step functions, you can think about instead partitions and then functions. So you can sort of define step functions based on partitions. Right? So if I have here a partition like this, well, you can turn this into a step function by looking at a function that is constant on the interiors of each of these subintervals. And then you can just choose whatever value you need in between. Okay. So instead of trying to look at arbitrary step functions, I'm going to access the notion of a step function this way. I want to look at first partitions and then step functions subordinated or adapted to the step function I need. Partition of alpha beta. As before, for calculation purposes, I'm going to look at the cut points. So these are going to be like x0, x1, x2, and so on. I can assume, as before, the lengths of each of these pixels is they are positive. So I have this case. As before, since I'm assuming that f is Newton integrable, I'll take an antiderivative, capital F, apply mean value theorem to it on each of these pixels. I have that for any I from 1 to n, there is a point, Si, in between. Such that the rise over run is f prime at that point. As before, I have this. And instead of uppercase F prime, I can just write lowercase f. And this is the length of this interval. Okay. Summing over all i's, again, Newton cradle gives me that the sum of all these terms is going to be capital F of beta minus capital F of alpha, which notes that even though for each I, this certainly depends on capital F, when you add all of them up, the total sum doesn't depend on capital F. This is the same thing as the sum of all of these terms. Well, I'll write it like this, it's faster. OK. So far, this is pretty much the same proof that we used for item 3. We sort of interpreted this right-hand side as the Riemann sum associated to a sampled partition. But now I don't want to do that. I want to this time use a step function. Okay? Let alpha beta, let sigma be a step function adapted to curly p. That is to say, it's a step function such that on the interiors of each of these intervals, it's constant. Such that for each I, sigma restricted to xi minus 1 xi interior is constant. Maybe I should say for each I, there's a yi such that for any, yeah, I'll write it like that actually. It's better. For each I, there's a yi, real number, such that for any x in alpha beta, if x is strictly between xi minus 1 and xi, then sigma x is yi. I'm just saying that I have this partition here, and I'm looking at the step function that is constant on each of these pixels, except at the endpoints. That gives you a step function. Then what I want to do is, well, you see this time I'm trying to compare the Bourbaki integral and the Newton integral. I can approximate the Bourbaki integral using step functions, or rather their integrals. So I can write it like so. Start like this. Well, even before that, I should say this. This was something that we used quite a bit. No matter which integration theory you use, the integral of a step function, everyone agrees what that number should be. In this case, the integral of this specific step function is going to be pretty much this, except that instead of f of si, I'm going to have yi. Should be alpha beta. That's by definition. So I'm going to inject this integral into the difference between the Bourbaki integral and the Newton integral of f. Alpha to beta. Sigma of x plus alpha to beta sigma of x minus Newton okay. I can sort of consolidate this because I know that the difference between two Bourbaki integrable functions itself is Bourbaki integrable. And then you've shown in a previous problem set that the absolute value of a Bourbaki integrable function is also Bourbaki integrable, which means that you can consolidate these two integrals and then put the absolute value within. That would give you an upper bound. Then for this, well, I'm going to have to do something about that. So I'm going to have to expand this also. Yeah. Do I have time? I think I do. Well, if you want, you can interpret this as the integral of some step function also. So this is upper bounded by this plus, well, this Newton integral is the same thing as this, and this is this. Again, consolidating. I have this expression minus f of si in absolute value, and then xi minus 1. Okay. This is upper bounded by the C0 distance between f and sigma. So this whole thing is upper bounded by the C0 distance between sigma and f and the length of alpha beta. And this too, you see, this is upper bounded by the C0 distance again. Write it like this. Consolidating everything, I have that this is upper bounded by twice C0 distance between f and sigma times the length of alpha beta. We haven't used the fact that f is Bourbaki integrable by the hypothesis that f is Bourbaki integrable. There's a sequence of steps that converge uniformly to f, which means I can take this arbitrarily small. which means whatever it bounds is bounded by something that is arbitrarily small, therefore it has to be 0. In other words, the Bourbaki integral is the same thing as the Newton integral, as desired. Okay? And that's the end of proof of 2. I'm not going to prove 1 now. At this point, you can take 2, 3, 4, 5, whatever, and use whatever method you want, because so for 1, you can apply whatever integration theory you need. Okay. I'm sorry, I'm a little over time, but we're done with the proof of FTC. At least the first one. Next week, we're going to start with the proof of the second FTC, and then we're going to switch to Taylor approximation. Thank you. There's an attendance sheet somewhere out there. Please make sure to sign it.